we'll just get started here in a bit. All right, so first things first, I want you guys to help me answer these true-false questions that I have prepared for you guys, okay? So the first question is, a program must be contained entirely in one file. Is that true or false?
False.
Okay, can anyone tell me why it's false?
It can be defined with another function and used to call them something else.
Okay. Okay, so if we have a multi-file program, then we can have some file that contains other functions for the main file. You all agree with that? Okay. Okay, so how about this then? Number 2, an advantage of an array-based list over a linked list is the ability to perform random access.
False.
True.
Okay, so I've heard true and false, so
I read it backwards.
okay, so we're going to say true then?
Yeah.
And why?
Because if you're doing a linked list, you have to start at the head and go to each node. But if you're doing an array, you can call on each individual part of the array.
Arrays have contiguous memory.
Okay, so linked list you have to start at the head and go through all. And what did you say for the arrays? Who said that?
Contiguous memory.
Okay, arrays have contiguous memory. And what does that mean, contiguous memory?
That each element in the array is next to each other in memory.
Okay, so each element in the array is next to each other in memory. All the times. Okay. Does anyone have anything else to add to that, or? Okay. So number 3 then. In multi-file programs, you need to use the preprocessor command include file name to ensure the necessary code is linked together. True or false?
It depends on if it's in the same directory, because you said include the file name with the parentheses. Otherwise, it needs to be with the bracket things, the arrow.
Okay.
As long as your file is located in the same place as your file that you're trying to include, you can use quotes, but if it's not, you have to use the less than or greater than signs. So, like, I don't really know how you answer that question.
Arrow things.
Okay, so what if we say, instead of include file name, we say
True.
You would still need to know where the file is being.
okay,
where your
so
files are at.
so is that now correct then? Okay. Okay, so now you think it's true? Okay, so you think it's true now. Okay, so what does the angle brackets mean when we're doing the include? Does anyone know? The less than and greater than?
Outside the directory.
Does it mean it's from outside the directory itself, or does it mean it's in a specific directory? Do you remember?
With
The angle brackets, yeah.
that would mean that it's in wherever you have your default set to look, right?
So the default directory, like the default library directory, is that what you mean?
Yeah, like, because you can change that in code blocks, could you not? Like, you can change where you want to look for your header files. You can change that setting.
I'm not sure if you can change that in code blocks, but I would guess you could, yes.
Okay. I'm not entirely sure.
Okay, so Okay. So we said that the angle brackets will go to where our C library directory is and look for the header file there. So that means, what if we've defined a file in a directory that's not in one of those two places? Then we'd need this path to file that I added here, right? Okay. So number 4. A disadvantage of array-based lists is the difficulty to insert an element at the front of the list.
True.
Okay. Does everyone agree that's true? All right. And why is that true?
Because it would shift everything, it shifts all the elements. Well, that's why it's just like, it's an extra word.
Okay. So if we insert at the front of an array-based list, we have to shift all the elements to accommodate the new element, correct? Okay. Is there anything else that would make it difficult to insert? Or is that it?
Define the size beforehand.
Okay, yeah, so if you're inserting into a full list, that could be an issue.
You have to know like the name and address and everything. But to insert in a linked list, you just have to know whatever the first, like the one before it is.
Okay.
So you have to know all of its specific like, information.
Okay, so in a linked list, we just need to know the head nodes so we can go through all of them to find where we need to insert?
But like in the array, you know like exactly,
Where you need to insert?
yeah.
Okay. All right. Oh, geez, that was weird. Okay. Is that showing up on there? Yes, it is. We might just have to ignore that. I'm not sure what is causing that. Okay. Oh, no, okay. All right, 5, to dynamically allocate size for an array of 30 integers, we can write,
False.
we can write this.
Because it's supposed to be calc for an array, and malloc for a linked list.
Okay.
Those just set everything, initialize everything to 0.
Okay, so does this work then as well as calc? So could you do this to do it, or do you have to use calc? Okay. Okay, so this works. But as we said, we can also use this. And what did you say that that will do?
Calc initializes everything to 0.
So calc will initialize everything to 0.
It would be 30 comma line and size of instead of the asterisk.
Okay, so that would be like this, integer pointer a equals calc 30 comma size of int. Okay. All right, so then number 6, when dynamically allocating memory, we can assume that the malloc will work and that we will have no issue using the new variable.
False.
Okay, and why?
You have to make sure you have enough memory to create a new variable.
So we need to check that we have enough memory to create a new variable. So check that it was successfully created. Okay, and what can happen if we choose to ignore checking? I couldn't hear you, sorry.
Oh, runtime error.
Okay, a runtime error, okay. So if we don't check, we could get a runtime error. All right, so then 7. An advantage of linked lists is not being constrained to a specified size.
Kind of true. It's true within, like, you don't have to predetermine it necessarily within the same way, but you still have to fit inside the block. So it's like
Okay.
kind of true.
Okay, so we'll say true because for our purposes, memory should be large enough. So why is it that we don't have to specify a size for a linked list?
Because it's dynamically allocated memory.
So we don't need to specify a size because linked lists are dynamically allocated so they can freely grow. Okay. If I can spell. All right then. So how about this number 8 then? In a linked list, each node knows only the data it contains and how to reach the next node. Okay, and who wants to explain why it's true? Or why you said it's true? Or if you said it's false and don't think it's true, then explain that as well. No one?
There are two components to each node. One part of it just has the value, and the other part just has a pointer to the next node.
Okay, and that's all the information that the node itself knows? Okay, all right. That's all that's in there? The only member variables? Okay, all right. So, a linked list knows only the data it contains and how to reach the next node. It only has two components, the value and the pointer to the next node. If it was a doubly linked list, though, that wouldn't be true, would it? Okay, so a doubly linked list could go backwards. So the doubly linked list has a third component, right? Which is the previous pointer? Okay, so question 9. With a linked list, we can only insert elements to the end of the list. Okay? And we can insert anywhere in the list, right? And that's not true for arrays either, is it? We could insert anywhere in the array, correct?
You can, but it's still going to shift everything, so it's not not relatively easy to question. It's possible, it's just annoying.
Okay, so we can still do it with an array, but it's difficult to shift. Okay. So an advantage of linked lists as compared to array-based lists is the ability to insert anywhere in the list relatively easily. So what do you think? Okay, why is it false? But if we're treating the array as a list, don't we have to, if we're inserting something, not replace, but then shift all the elements? So would it be easier then to insert into a linked list instead of an array? If you have to do the shift? Okay, so true then? And why are we going to say it's true?
You don't have to worry about shifting all the other elements.
Okay. So we're going to say it's true because we don't have to shift every element in the list. So question 11. An advantage of linked lists is the ease of deleting elements from the list.
Yeah.
I hit the wrong button. Okay. True?
Yeah.
And so why is that true? Why is it hard to delete from an array list?
Because from an array, you can erase the value inside of the block, but you're not actually erasing the block. So each of the little blocks that you're creating inside of the array still exist. Whereas in the linked list, you can just get rid of the whole block altogether.
So with an array-based list, if we wanted to delete, it would erase the value in the block,
But not the block.
but not the entire block, leaving a blank space in the array, but we wouldn't understand this blank space, right? Because you'd have to give it some value, but you wouldn't necessarily know unless you avoid putting that value in the list that that's a deleted space, right? So it's infeasible to delete from an array list without shifting. Okay, so question 12. With a multi-file program, we can define a global variable in one file and use it in any other file that the file is included in. True or false? Okay. And why do you think it's true?
Because the definition just has to be stored somewhere, and as long as they properly use the R thing to file open R to read it out. If you pull it through properly, as long as it's a definition, the include statement you can pull it. But yeah, it has to be global. You can't the definition has to be outside of the int block. You're ready to pull it together in a file.
Okay, are we sure that we can use a global variable in any file the file is included in?
Oh, the variable? No, I thought it was a function. No, so that's false. You can't just use if you say int, n is nothing. It's not just int, and it's nothing forever.
Okay, so how can we use global variables between files?
Defining them at the top, pi or something,
Okay.
you do the pound sign include, but you do pound sign define, or you pull it from library.
So that would be for a constant, right? Sharp define is defining constants. So if we had a global variable that we wanted to use between multiple files, we would use the extern keyword.
Only in the other file, though.
Oh.
Not the main C file.
Only in the other file. Okay, so, all right. Anything else on that? Okay.
So what you're saying is if you do extern global variable in another file, you read it into your program, you can use it to file number 3.
Right, so if it's defined somewhere with extern and in another place without extern, it can be used in both those places. Okay, so 13. You do not need to define a function completely in one file. You can split the definition of the function between multiple files.
False.
Okay, why is it false?
So the definition has to be all together in one. You can't split a definition up.
Okay, so that's false. We can't split up the definition. It has to be together in one file. It would not compile if you tried to split it up. Each file needs to be able to compile on its own in order for a multi-file program to work. So question 14. Statically allocated memory is created at compile time.
True.
Okay, so true. The compiler will go ahead and create those variables for you. Okay. So then how about 15? Dynamically, okay, so dynamically allocated memory is created at compile time is false.
It's runtime.
Created at runtime. That's why we call it dynamic, right? Okay, so 16 then. Dynamically allocated memory is only accessed or accessible through pointers.
True.
So we're saying that that's true. So why is it true that it can only be accessed through pointers?
That's how the little blocks of memory are connected. Like when we draw it out, that's what the little arrows are, is it's pointing to the next one. That's how the nodes connect. Like that's how they make their chain.
Okay.
Otherwise they are just kind of floating there, so they need to point to like make a link.
Okay, so that's specifically with linked lists, right? With the nodes that they chain together, which that's an example of having dynamically allocated memory, correct? That's going to have pointers to the memory because when you're allocating dynamically allocated memory, you need a pointer, right, in order to create the variable. For example, we have int a pointer from above, or int pointer a from above, which was equal to malloc 30 times size of int. This is a dynamically allocated array, and see how we use a pointer to define it. So we obviously need a pointer to access it because we can only define it using a pointer, since dynamically allocating memory requires knowing where the address of the variable is going to be created at. And 17, the size of operator returns the amount of memory used by the data type.
True.
Okay. So we're going to say that that's true. The size of operator returns the amount of memory used by the data type. So if we said size of int, we would get typically how much?
4.
Okay, so this would typically be 4. All right. So then another question on the size of operator. Size of operator is evaluated by the compiler.
True.
All right. So since it's evaluated by the compiler, it's not exactly a function or operator. It's just a compile directive, more so. But we're going to reference it as the size of operator or size of function. And does anyone know why it's evaluated at compile time?
Because that's when it's done adding all the stuff that needs to be added to it.
Okay.
That's when it's finished.
I guess, yeah. Maybe that wasn't a good question, because anyone theorize maybe would be a better way, because I don't believe he said it. So I guess this is beyond the scope of the class. But the compiler knows the amount of space that's allocated to variables, not the actual language itself. Okay, so then 19. free is used to deallocate dynamically allocated memory and return it to free memory. And so using our array that we keep defining above, A, what's an example of using the free function? Okay, so that's how you do it, right? You call free on a pointer that's dynamically allocated, right? Like that, just like that. Just needs one thing. Okay. Question 20 then. Free can be used on statically allocated memory as well. True or false?
False.
Okay, so false. We have one person saying. Anyone else have any thoughts on it? Okay, so everyone thinks it's false? Does anyone know why it's false?
If you were to freeze something in contiguous memory, then that block of memory would no longer be contiguous.
Well, is it a problem with contiguous memory as to why we can't deallocate a statically allocated variable? Or is it perhaps to do with how it's allocated?
We use free to like erase the pointers using statically allocated.
So that's kind of right, yeah. I mean, again, it's a bigger picture kind of thing. It just doesn't work because it's only defined for dynamically allocated memory. Since that's what's defined at runtime, it's the only thing that during runtime you would have the ability to clean up. Everything else is handled by the actual systems software, which you can't control. Question 21. A memory leak is when you do not free memory, but you no longer maintain a pointer to that memory, effectively losing it. And what's the problem with forgetting to use free and having these memory leaks occur?
It's taking up space on the processor computer. We potentially use for other programs.
You wrote free and said true or false.
Thank you.
Yeah.
My caps lock key does not want to work. Okay, so it's true. Taking up space in memory. So you can eventually run out of memory then?
Yeah.
Excessive memory leaks in multiple programs that are running at the same time can lead to memory bloats in your system, which is one of the main reasons why you want to avoid it, as well as being able to cause runtime errors for running out of memory. Question 22. Null is a special value that indicates nothing is being pointed to. And null is only usable with pointers, correct? And it's different than saying 0. Okay. Dereferencing a null pointer does not cause any issues.
False.
And so What kind of a problem will it cause?
It'll crash.
Okay. And what are cases where we might need to be checking for null, where we could effectively have this runtime error if we're not careful?
The end of the list.
Okay. All right, the end of the list. Opening files, is that what you said? Okay. Opening files, dynamically allocating memory. There's probably more, but that's the basics of it. Okay, 24. Functions like fopen return null to indicate success. False, okay. What does null indicate? So it's a failure condition, right? If it returns null. So if this statement instead had said functions like fopen return null to indicate failure, what would the answer be? Okay. And what are some other functions that will return null to indicate failure?
Looking for something on the list that they never found it.
Sorry?
If you're looking at like a search function, and so it searches the list and
Okay.
it's not there, so it returns null because it never found anything.
Okay, so a user-defined search function? I didn't hear that one.
String compare, like
strcmp.
I think it returns null when two strings don't match.
What does string compare return? Does everyone remember the return type of that?
0 if it's the same. And
Okay.
any other number if it's not, I think.
Okay, what is it?
Something like that.
Okay. Okay, so string compare is not one of those functions that returns null to indicate failure. EOF. Does that return? I'm not sure whether or not that returns null.
I never got to work using null or anything. I couldn't get the end of file to work.
Okay, well, I guess not then.
I'll double check real quick. But
You can look up what the end of file will return if you go to C++ reference or something like that, and then we can add that there if it's definitely going to return null. Any other functions?
It just returns false.
Okay, so it returns a Boolean value of false. Okay. So then what does return null to indicate failure? Okay, malloc. Anything else? Calloc. I don't know if we know anything else. Can you guys think of anything else? Okay, then I guess that's it for what we've learned. Okay, 25. Calloc is a function specifically for allocating arrays. So if I wanted to allocate an array of 30 integers, how would I do that with calloc? So what comes first? Okay. So that would give us that would return a pointer to the first block in a 30 block integer array? Correct. So a malloc would look like this, yes? That's correct if it was a malloc, right? Everyone agree? Okay. All right. Next, calloc will initialize memory to zeros.
True.
And while we're here, what does calloc stand for?
Contiguous allocation.
And what does malloc stand for?
Further allocation.
Okay. And there's actually another allocation function. He mentioned it, but you don't have to know it, so never mind. I won't have you guys do that then. Inserting into the middle of a linked list is a relatively easy operation when compared to inserting in an empty list at the beginning of a list and at the end of a list. Okay, false. And why is that false?
Because we need more information in order to do that.
So inserting into the middle is a harder operation?
Yeah, it takes more information.
And why is it a harder operation?
Because you need to know more stuff, like to put ahead of a list, you literally just write like 2 lines, versus to do that, it would take like the whole thing.
Okay, so what kind of things would we need to know?
In order to put it in the middle of something, you have to know what the head is and then what the true spaces, values at before and behind it are.
And we need to know where to insert as well, right?
Yeah.
So it's harder because we have to know the head to find the list. We have to know where to insert so we can find what's before and after. Or if we know what's before and after, we can insert knowing that.
And finding the before and after, you would have to traverse those.
Okay. So finding the before and after elements requires a traversal of the list, which can be time consuming if we have, say, 1,000 elements. Okay. Question 28. When deleting a node from a linked list, we need a pointer to that node so we can free it once we are done removing it from the list. Okay. So, it's true that when we're deleting a node from a linked list, we need a pointer to that node so we can free it once we're done removing it from the list. Okay, so can someone describe the process of deleting a node from a list?
You just put your arrows around it. It's just kind of like you're taking whatever's pointing to it and you're just kind of like redirecting it to point around it like it's not there.
Okay.
So whatever the temporary one that is holding on to it is, it just kind of like pulls it away. And you delete it, I guess.
Okay. Someone was whispering something. What did you say?
He was asking if that's
No, I couldn't tell if it was an equal sign or.
Oh, okay. I just wasn't sure if you guys had something to add to the description. Okay, so we need to take the pointer that points to it and redirect it to point around it and keep a pointer to that one so that we can free it. Okay. So if we were to draw it out, you'd just have the arrow and move it to the next one and then erase that.
Yeah.
Okay. Okay. Doubly linked lists are a special type of list where the nodes point to both the prior and next nodes. Okay.
Yeah, true.
So what are the components of the node struct for a doubly linked list then?
Head, current, and tail. Like you mean like what goes inside of there?
Yeah, what are the members of
Int
this?
number or like int value, so it'd be like the value for it.
Okay.
And then you've got to have the tail one, so it's got to be like, yeah, node pointer.
struct node next.
Okay, so next. And then what else do we need if it's going to be a doubly linked list?
We need the one before it, right? So we need the previous
Okay, so struct node pointer previous. Okay, so this is how we define a node for a doubly linked list. Struct node with the members of integer value, struct node pointer next, and struct node pointer previous.
If we're going to initialize it, we could put node after the curly brace before the
Type
semicolon.
check, yeah, you need that, because you can make it a type.
So this is so we can create a type for it.
And then there's another line afterwards that's like type def.
Yeah, type def node pointer, node pointer.
Okay, it's not necessary, but yeah, you can do that.
Well, in order to access the, oh no, if that's only if you want to use, make new ones, like to make the header, like the temporary one.
Like that?
Yeah.
Okay. All right, so, and then why is a doubly linked list special?
Because you can go to one beforehand.
Okay, and does that make insertion and deletion easier?
Yeah,
Okay.
because that way you have to start at the front, like, you can work backwards instead of having to go up every time.
Okay. All right, then the last question for the true and false. Is this true or false?
False.
Okay, so what would be true then?
Or one equal sign?
8, 0.
Oh, 0, yeah.
So this is correct, right? And is this correct as well? Is that correct too? Okay, so we have some people saying yes. Okay, so yes, those are both true. So that is 2 ways we can fix that statement. So that was all for the true-false questions. If you guys didn't get anything, you can go back and look at the video online. If you did get everything, then that's good. Now I'm going to pull up some code because I have some code questions for us. Let's start with the first problem. This is going to require a bit of working around things to have it visible, but that's way too big, right? Okay, let me just go into the settings and adjust the size of it because I didn't know how big it was going to show up on this. Is that going to be legible?
Yes.
Those of you at the back, can you read that size font?
Yeah. You do it as a little, like, one side.
Okay. That good?
Yeah.
Okay. All right, we might be able to get more of it on the screen with this then. Okay, so here is some of the code because it's not all fitting on the screen. So this is the main function, and I want you guys to scan through this for a few minutes. I'm going to give you like a minute right now to scan through it, and then I'm going to help you guys scan through it. Does anyone have any idea of the output yet?
You're making a random list, and then you're erasing them afterwards. You're saying your list has, I guess, if 25 elements that are allowed to go up to 50. There's a for loop that creates.
Would it be 25 or 26 elements? People are saying 26, some are saying 25.
The make random list is 25, so I guess it's 26 is the first one to add.
Okay. Okay. Well, let's trace through it then. Let's do a little bit of a trace through this code and see what we come up with. So in this line here, node pointer mylist equals make random list 25. We're calling this function here the make random list function. Okay. So in this make random list function, we're creating an integer variable called I, and then we're going to create a node pointer that's null so that we can start building the list. And so it's just going to create, it's going to run through this loop to create random nodes. So how many times is it going to, that's what we need to be concerned about. How many times is that for loop going to execute?
It's 25.
Okay, so it executes 25 times. And why do we know that it's 25 times?
Because in the list where it says make random list is 25, 50, and 25 is where you put the size, and then the max is like the max value of the number. So it's 25 numbers up to 50.
Okay, so by using the understanding of what the code should do, we can say that it should be 25. But then if we look at our for loop, how can we say that we know that the loop is going to execute 25 times?
Because it says I to size. So
Okay.
it's going to go on until the counter variable does it 25 times, or however size times.
So, okay, so counting from 0 to 24. Okay, all right, so it'll execute 25 times from 0 to 24. All right, so we have 25 things on our list. So then we're going to go to this function up here, which says printf my list has %d elements, num nodes my list, which right here is going to go down and call the num nodes function, which as you can see has a counter variable, and then it's going to do a while loop and until we reach the end of the list. Is that what that's going to do?
Yeah, that's what it's all.
Okay. So if it's going to do that until the end of the list, what's the value of count going to be when it's returned?
25, or whatever the size it puts in. This case 25.
So it's going to be 25? Okay, so if we go back here and we're returning 25, what's the print statement going to output? Okay, let's see if we can get that output. Let's see if we get that output when we run the code. Okay. So, touchy. Okay, so let's do the second problem. Oh, I need to change something real quick before we can test it. So second problem. So I'm just going to scroll down past the include statements and the struct definition. Just assume that that's done correctly. Okay, so what do you think it's going to print?
I think it's gonna like print it out like backwards or something.
So linked list fun text world hello.
I think so, because of like it keeps redoing itself as the head value,
Okay,
so it's like adding it on to like
the front.
front, I think.
Okay, so it's
So
inserting.
add it on to the front and it's moving forward.
So it's adding to the front.
I think so.
Okay, so then let's trace through it again. Let's jump to this insert function. So this line here, what's it going to do? This one right here where I put the comment.
Allocate the size.
Hmm?
Allocate the size of the node.
So allocate a node. So then what's going to happen in this next line?
That adds the string onto the, but yeah. No, that copies it, so it replaces. Yeah.
So it's going to put that value of the string into the node, right?
Yeah.
Okay, so then what happens here?
It's saying that the new next value is now the head.
Okay, so new node's next is head. And then what happens here?
The head's pointing to new.
Okay. So would that mean that every time we do it, we're going to add it to the front?
Yeah.
Okay, so let's run it and see if that's what happens. Does that make sense? Or do you need me to, like, physically trace through it or something?
Placing it on the front of the list.
Right, so it's updating the head every time you insert, right?
Yeah.
So it's placing it at the front of the list? Okay. You ready for the next problem, or does anyone need to? Okay, 42 and 43. So the new dash next equals head and head equals new part. So what about it?
In my head, it feels like it's going to start.
Okay.
I don't know that you're trying to say.
Okay. So if we take the value of the new node and we point it to the current head, then the next node that comes after that is going to be the first node in the list currently, right?
Take the data and points in that. Yes.
So then if we take the head and then update it to the new node after linking the new node to the old head of the list, we're going to have the beginning of the list be that node that we're just inserting.
So we're creating a list from the front back.
Right, we're creating the list back to front. So it's an insert at the front of the list function to create the list from back to front. Anything else, or are we good on this? Okay, I'm going to skip 3 for now, and actually no, I won't. I'll do 3. Okay, so we have problem 3 now. This one's a bit more complicated, but it's a modification of the last problem. Okay.
What happens when you're putting ampersand head into sorted insert? We didn't do that in our class. We just put in, like, for example, we just put in head. What happens when you do that with a struct?
Okay.
That's save value.
So do you remember what the ampersand operator does?
Well, I think that's passed by reference. It's normally saved values you change to that function.
Right, so it allows you to change it in the function that you're passing it to.
So that's just the same thing with struct.
It's just a pass by reference, right? So it just gives us access to the. Well, what does the ampersand operator actually do? That might make it make more sense. Does anyone?
It's a referencing operator, so address of whatever variable.
So it passes the address of the variable. And then do you see how this this function is defined to be a double pointer? So it's expecting a pointer to a pointer. So if we pass it the address of the pointer, then we have a double pointer. We have a pointer to a pointer, which allows us to make modifications to that original pointer, which was necessary when trying to update the value of head inside another function without returning it. Since it's a void returning function, to modify the value of head without returning something, you have to So this one, again, like I said, is more complicated. I'm going to try and let you guys see all of this. The only thing that's different from the last problem is this, so I want to try and let you see all of it.
Is it just kind of saying if the word is shorter to put at the end? Is it organizing the words by the size?
What does string compare do?
It's based off the value, right?
It's how do we compare strings?
By their size, like, because an int is like 4, and then a character is like something.
So when we're comparing strings, do we compare it by the size of the string or lexicographically?
Strings is by length, right?
Okay, so it's going to be an alphabetical ordering of the strings. So if we're using string compare to do that, then it's going to sort it alphabetically, correct?
But does it still start? Because before the if stuff starts, like in your while statement, it's just saying if the current one is to null, then you print that one anyway. And I think it starts out, wait, as long as the first one doesn't, never mind.
So do you guys, does anyone have an idea of the output, or do you need me? Well, I mean, I will trace it, but does anyone have an idea of the output? Okay, all right, well, let's trace it through. So, well, let's trace it through and find out, okay? If it was in alphabetical order, what's it going to print out?
Fun, below, linked list, text world.
Okay. So now let's go through. So when we call sorted insert with the first time, our head is currently going to be null, correct? So it's going to go through this statement. So that's going to insert hello at the front of the list. Because it's an empty list, so there's only one element. Now when we go to world, head is no longer null, so we're going to jump into this. So then we have this if statement here. We're going to string compare the value of the current head with the string. So the current head is? Okay, and the string is? Okay, and what's the return value of string compare going to be if we got hello and world? So what's that return going to be? Is a negative number less than 0? Okay, so we're going to go into this if statement. And so in this if statement, we're going to create a new node here, correct? And so where are we going to insert this new node that we're creating? So is it going to become the new head of the list?
Yeah.
So now after that, what's our list going to look like?
World below.
So that's our new list, right? So then we're done here because that's an else. So now we're going to go back up here. And then we're going to call it again with text. So let's jump in here. And we've got this string comparison again. Is we have world. So what's the return value of this?
That's comparing the world to the word.
So what's that going to return? Okay, so that's going to be a positive. So we're not going to go through this if statement. So we're going to go to this else statement. I think I just said elf instead of else. Else statement. So now we're going to create a trail node and a current node. And then we're going to go through this while loop. And so the list is currently so I want you to tell me where the current and tail are going to be pointing when we exit this while loop.
Question. When does it how do you know if it compares, if it returns positive or negative string compare?
Okay, so does anyone want to answer that? How do we know what string compare returns?
It tests for alphabetical order. So if the first one is first in alphabet, it'll be negative. But hello is capitalized. Capital letters come first before lowercase letters. String compare.
So how we're determining whether it returns positive or negative is whether or not the first one comes before or after the second one in the alphabet.
So in this, the trail becomes the head, which points to new, which points to current. So it goes trail, new, current.
Trail, new, current, what?
The thing, tail, whatever that word, trail.
Okay, what is trail going to be when we exit, world or hello?
Say what?
What's it going to be pointing to when we exit the while loop, world or hello?
Which one did you put?
Trail.
Trails, the new head, so it's going to be the one we put in, it's going to be word base added. So
Okay. All right. Better way to put it then.
world, I guess, is the first, is above.
Okay, so
World is going to be before hello.
so let's start up here then. Node pointer trail equals head. So what's the value of that?
When that starts.
Yeah, when it starts.
World is the head of the list.
And then node current is head dash next. So what's that? So hello is not null. So we're going to go through that and statement, right? So what's the return value of what are we inserting?
Back to text. Yeah.
So
Yes.
keyboards don't like me, I'm sorry. So negative? Okay, so if it returns a negative, are we going to continue with this loop or are we going to exit?
Exit.
Okay, so we're never going to go through that loop. So we still have trail pointing to world and head pointing to hello. So now we're going to create the new node. And where is it going to get inserted?
After new. Then it says news next points to current.
Right, so new dash next is going to point to current. And what's current? So current's hello. So our list, when we get to this point, is going to say, what's the list going to be now? Now that we have the 3 elements in it. So now we have world text hello. Okay, so now we go ahead and we're going to try and insert fun. I mean, I hope you guys are having fun. So now we're going to try and string compare right here. World and fun. So what's that going to be again? So we're not going to go through that if statement. We're going to go back down here. So this is going to start at world this time, and then what's this one going to be this time? So then this string comparison is going to be, what are we, fun, yep. So what's that going to return? Okay, so if it's returning a positive, are we going to go through the loop? Okay, so now current equals current.next dash next, so what's current going to be? And what's trail going to be? And now we're going to do this string comparison, and what's that return? Okay, so now we're going to go down here, and where are we going to insert fun? Okay, so right here. Okay, so then we're going to take that back up here. Then we get into this one. We're going to insert list. Okay. What's our current head? Okay. And so what's our trail going to be? Okay, still world. And so this time, what is current? Sorry, that was trail. What is current going to be now? I think I said current for that one. I don't know. Okay, what's current going to be? Okay. And so we're going to compare. Okay, and what's that going to return? Okay, so if that's positive, what are we going to update current to? And what's trail going to be?
Wasn't string compare hello fun supposed to be positive?
Okay, capital letters come first, so, well, that's what we've said, so that's what we went with, so we'll see when we run it. So now we've updated this, so now we're going to compare fun and list, and what's that going to return? Okay, so if that's negative, where are we going to insert list? Do we insert, so look at where we're inserting it. What we update new.next to be current. So what is our current? Is current text or trail? Fun. Okay, so the current's fun. So if we're pointing current to fun, we're going to update new-next to be fun, right? So it's going to point here, and then we're going to update trail, which is text, right? So that's next is going to be new. So we're going to put list right here. I know this one's hard. So that's our new list, right? I know this one's hard, but it's good to trace through this because if you can follow this, then you should be able to do any of the questions he puts on the test. Okay. So now we're going to insert linked. Okay? So the last one. We're almost done. So what's our head still? Good. What are we inserted? Good. That's positive? Okay, so we're going to move back down. So world is our current head still, right?
Yes.
And then our next is still text, right?
Yes.
Okay. And so we want to compare text and linked, which is positive. So then we're going to update them again, and so it's going to update to fun and text, right? Or no, actually, sorry, not fun. What is it going to be? Okay, list and text. Now we want to compare list and linked. Okay, negative. Okay, so we're going to exit there, and where are we going to insert linked?
Which one did you say? List and list, that's positive.
Okay, it's positive. We have people saying positive and negative.
Positive. I thought you said list.
Okay, it's positive. Okay, so if it's positive, current's going to be what?
One.
Okay, now if we compare fun and linked, what do we get? Okay, so now where are we going to insert linked?
In between list and fun.
Okay. Okay, so now we have that, right? So now we're going to print that out, right? So let's see what we get. So I know that one was hard, guys. I made that one hard on purpose. I made that one hard on purpose, and I know there won't be anything as hard on the test, but it's good to do something harder than what you're going to see so that you'll be prepared for what you're going to see.
You'll be able to send this question to us so we can answer this after this session.
The session is streamed, so you can find it.
Back to the stream.
Yeah, you can go back to the stream and look at it.
What's the website for this room?
It's on YouTube, but you should be able to find it. Yeah. Okay, so now this is problem 4. I promise that none of the others are as hard as that one. Okay, so take a few minutes to look over this and figure out what it's going to output. A piece of paper might be helpful because you might want to do math. I don't remember how much math I put in it. Correct. The A will point to the first element in the array. I'm just going to give you guys a hint just in case anyone gets stuck here. Don't forget that these are true statements. Don't forget that. Okay, I did not catch all of that, but
Factors of 25.
30, 54, 25, 50, 75,
Stop at
100, 125, 150.
It's gonna stop at 86.
So is this,
1, 2, 3, 4. So the last one would be
is this 175?
no, not 0. I think 0 after that.
Okay, so you think it's like that? Is that 10 elements? Okay, that's 10 elements. So that's what you think the list is? Yeah? Okay. Did anyone else get this? It's okay.
No, because it's not 8, 7. It's not gonna get to 7 because it's high enough than 7. It's not gonna get to 7 because it's high enough than 7.
So how many times is this loop going to run?
6.
So it's going to run from 1 to 6, right?
Yes.
Okay. So what's the value of n?
10.
So what's the value of n times 2.5? So we have 25 times I, so it's multiples of 25, right? Okay. So positions 1 through 6 are going to be the multiples of 25 from 1 to 6? And then beyond that, zeros?
Yes.
Okay. Let's run it and see what happens. So as we can see from this here, we can generalize this right here. These dereferencing of A equal to A sub 0, we can generalize that to be this, right? Right, we can generalize and say that for any value of I, adding it to A before dereferencing is the same thing as using the array notation. Does anyone remember why that works? Why is it true?
Do the name of it,
Okay.
and the name of it is the first one.
Okay, so if we point to the name of it and the name of it's the first one, what happens when we add 1 to that value?
But you're not you're adding 1 to the length value though. Like you're going down the list, you're not adding it to the actual.
Right, so what happens when we add, oh yay. Okay. So what happens when we add 1 to it? When we inside the parentheses there? This isn't good. Okay. I think I just have to hold it. So we add 1 to the memory value, right? And what does 1 to the memory value mean?
It goes to the next place in memory.
Good.
Are you trying to?
No, it just keeps going in and out. Oh, it's back now again. I don't know. It's just being finicky.
Try not to do this.
Yeah.
Okay.
Okay. Hopefully that'll stop being finicky. All right. So as we see, we add 1 to A and we get the first index, or the second, the A sub 1 of the array, right? So if we want to add 1 to that, before we dereference, we're saying we're adding 1 to it, but what does that actually mean? Okay, so it means move 1 space. So what's the actual value?
You're adding to the length, you're not adding to the name,
Right.
right? So it's actually a bracket 1. You're saying array move over 1.
Right, so we're adding to the address. So when we do address math or pointer arithmetic, what does the +1 mean?
Move 1 to the right.
It means move 1 space to the right, correct? And so if we're talking about integer spaces, what is the length of that space? 4 bytes. So when it says A plus 1, it actually, the +1 means +4 bytes. because it specifies the amount of spaces to move, which will just automatically multiply by the size of the data type when it calculates the arithmetic. So, okay. Any questions on this? All right, good. See, I told you they weren't as bad as the other one. Okay, so problem number 5 then.
Did you take these off of this website? Is that why he has the comments at the top?
I did take this one off the website, yes.
Are they like on his like top 32 website?
This one is from the solutions to the problems posted on the syllabus. So if you guys have done the problem, can any of you tell me what it does? Or if not, I mean, look through it and tell me what it does. And this is the delete last function in case you need to see that. I didn't realize it wasn't on the screen, sorry. So, does anyone have some idea of what's going to happen?
Making a list and then deleting the last thing from the list.
Okay. All right. So do we want to trace through this then? All right. So right here we call make list with values of 10 and 100. So let's go down here. So what happens with this loop? It's going to run from what to what?
It's going to run from 0 to size, and size is going to be 10.
Okay.
So 0 to 10 times.
Does it go? Does I get to 10 or not? Okay, 0 to 9. So what's this statement going to do every time?
That's going to set aside the memory to block.
Okay, so we create a new node here. So or set aside dynamic memory to create the node. Okay, so what's the value going to be for this?
I cubed.
For the first time. Okay, so I cubed. And then what's this going to do with it?
That means that the number can be percentage. So
Okay, so it's modular division. Okay. So I cubed mod max. What's max? So what we have is this, correct? Okay. So when I is 1, what's our value? Okay.
Well, yeah, 'cause
Sorry, I forgot. We should start at 0. When I is 0, what's our value?
0.
So 0. Okay. And is that going to be, that's going to be the first thing in the list, right? Okay. So now I is 1, so what's our value? 1, okay. And where is it going to be in? So is it inserted after or before? Just, you know, be careful.
The next one is at the front, so it's actually
It's going to be inserted at the
Okay, so we're inserting, so he says we're inserting at the front. So let's go through this then. So new dash next, so our new is currently 1, right? So new dash next equals front. So what's front right now? Okay, so new dash next is equal to 0. And then front equals new, right? So then this is where front points. So it's going to the front of the list, isn't it? Okay, now when I is equal to 2, what are we going to get? Okay, and where's that going to be inserted? Okay, and where's that inserted? Front. Okay, so 8 at the front of the list. Now when I is 3. Okay, 27 inserted where? Okay, they're all going to be inserted at the front?
Yes.
Okay, so what do we get when I is 4? 64? And 5? 25, okay.
It's after 27.
Wait, what?
Cube is 125.
Cube is, it's 120, 125.
Mod 100.
Just goes into 125 one time and you have a remainder of 25.
Forgot about that.
So the answer is 25.
So 125 mod 100 is 25. Okay. Now I is 6. 16. And I is 7. 43. Okay. And then 8. How much? 12. Okay. I don't know if you're correct because I can't do that off the top of my head, but I'll believe you. 29? Okay. So these are our values, right? So it's going to be in this order, correct? So I'm just going to copy that. We're going to exit out of here, and we're going to bring this list back up here. So first thing we're going to do is we're going to print the list, right? What? Oh, I'm sorry. I thought I must have messed something up. So here we print the list, right? So we're going to get this whole thing printed out, correct? Right, this print. So then we're going to go into this loop, and how many times is it going to run? How many? Okay, 10 times. And the values of I are going to be 0 through 9?
Yes.
Okay. So then what happens when we call this delete last function? Let's go down and look. So we have, this is our list right here that we're passing to it. So let's look at what happens. Is front null? Is front dash next null?
No.
Okay. Okay, so this is going to be equal to front, so we're going to start this at 29. So then what do we do?
You're assigning it to, like, okay, so you're pointing the temporary value at it first,
Okay.
and then you're freeing it. So you're saying temp and temp next are both pointing to this, and then you erase it once you move the other stuff.
Okay. So where's this going to go? What are we going to remove from the list?
29.
Are we going to remove 29 from the list?
The next is temp next.
So we have this while loop that's going to go through until temp dash next is null. So what is temp going to be when temp dash next is null? 0? Where's temp going to point to?
If temp dash next is null.
Right, so if the node after the next node is null, where is temp going to be? Okay, so we're going to say it's 1 when we exit the loop. So it's 29 at the beginning, and it's 1 when we exit. So if it's pointing to null, what node are we freeing when we call this function right here? So what's temp dash next? Temp dash next is 0? Okay, so we free 0. And then we make 1 point to null. So now we have to update our list. And this is going to be our new list, correct? So then we're going to print that, right? So then we're going to go back to the beginning of the list. And then what are we going to remove this time?
1.
Then we'll print that again, right?
Yeah.
Then we'll go back. And then what are we going to remove? Print that, and then, okay, remove 27. And then we print that, and then remove 64, print that. And you get the idea. We're going to keep doing that one by one until the list is, will it take out the 29? I'm not sure. Let me go back to the function. So if front-next is null, we don't do anything, right? So once we're at 29, what's going to happen? Are we going to remove it or not? Okay, so let's run it and find out. So it should iteratively remove 1 from each time we print it, right? There we go. Okay, well, apparently it does get rid of the 29. I'm not sure why, because front next should be null, which it says return null, so I'm not sure why, but.
Would it be because it sets my list to what it returns?
Ah, yes, there you go. I was not watching that you had my list equals, so you are correct. It is because you set it equal to the return. But then you would not be freeing something, and that's bad. So there is a memory leak in this code, because they did not free 29. Do you see that? Okay. So, but this makes sense? This is what we got, right? This was the list we came up with? Okay. Anyone have any questions?
Where is the memory leak?
Okay, so see how here when we have 29, we're going to initiate this loop, right? Because 29 points to nothing, points to null. So when 29 is the only thing in the list. So when we have this list, just this, 29 points to null. So front dash next, or front arrow next, or however you want to say it, is null. So this if statement will happen, and we're going to return null. But we never freed the 29. So that's a memory leak, because we didn't free the 29. I mean, it's not going to be a huge deal, because it's not going to cause us to crash from running out of memory, but it does consume extra memory and leave that block floating with nothing to get to it.
Can we just make it return just front instead of stop?
So you'd need to modify it to have two if statements to say if front is null, then return null, and if front dash next is null, free front, return null. That's how you would fix it. So instead of this, you would say so you would change it to be like this if you wanted to get rid of that memory leak. So that would eliminate that memory leak. Do you see how that would now take care of freeing that last element? Okay, good. You probably won't need to micromanage like that for the test, but it's important to understand that that would have caused a memory leak.
I have a stupid question. Can you go to line 50 with that?
Sure.
So for the modulus there, so in the first for loop,
Okay.
line is 0, right?
At the beginning? Yeah.
So 0 modulus 100. Wouldn't that mean like 100, how many times 100 goes into 0? Which is 0 times, but like the remainder is 100?
So what's left over when we divide 0 by 100?
Wait, 7 goes into 21 3 times and there's 0 remainder.
Right, because
So
it's
0.
perfect.
But if I is 0, modulus
So,
100, isn't there 100 remaining?
so how does modulus work is what would answer this question. So I cubed divided by 100. So what's that going to be? 0 divided by 100. And what's the remainder of that division? If you had a 1 on top, you would have a 1 left over because you'd have a decimal remainder, right?
The mod function, the mod function is your numerator minus the numerator divided by whatever you're dividing by. No, yeah.
Yeah. So, yeah, that's another way to look at it. That might be better. So, our remainder is going to be I cubed times n times minus n times 100, where n is the amount of times that 100 goes into that number. So how many times does 100 go into 0? So what's 0 times 100? And what's 0 minus 0?
Okay. I think it's just the 0 that's messing up.
Okay. Anything else? All right, then let's move on to the last one. We have just about enough time to do it. Oh, that's the first one, not the last one. All right. So this is the last one. So again, we're going to be working with linked lists. So this is not necessary. We're not doing random numbers. I forgot to remove it. Okay. So this is the code. So have a look at it for a few minutes, and then we'll go through it.
So it makes a list of 10 nodes that can go up to 75.
Okay.
And it adds them to the front of the list.
Okay.
And then so it prints it forward and then it reverses it.
Okay. Let's look at the entire back to front function just to see whether it's going to reverse the entire list or it's just going to move one node or something like that.
Placing nodes at the front of the list.
Okay. So let's trace through it real quick. So we think what's going to happen is this is building it back to front, and then this is going to move. How many nodes is it going to move? This back to front function, looking at that.
Just moves the front.
Does it move just one node from the back to the front, or does it move multiple nodes?
There's a file moves all the way to the end of it.
Well, does the while loop move things, or does it just scan? Or traverse, rather?
Taking in the front value.
Okay, so it just traverses. So if the while loop's just going to traverse, if we look at the new front, it's just moving one thing from the back to the front, right? Okay, so if we're moving one thing from the back to the front, then we are only moving one thing, not reversing the entire list. So let's keep that in mind as we go through this. So we call make list with 10 and 75. So let's come down here with 10 and 75. I really should have just done the same thing I did for the other problem to make things easier, but I didn't. So this time, that's not necessary. This time, this is what we are going to do with the value. So what is that going to be? Just convert that into math for me.
10I squared mod 75.
10I squared, that's not a squared, mod 75. Okay. So let's build the entire list. What is it going to be? What's I at the beginning? Now what do we do when we have I of 1? 10, okay. And then what comes next? 40. And then? What? 15, okay. I'm sorry, I thought I heard 50. I was like, I don't think that's what you said, but. What? 10 next, okay. And then what comes now? So now we have a 25 inserted at the front. It's not a big deal if they're off by a few numbers because it is difficult math, but 60? Next. So 40 now at the front, and then what do we have now? 40 again. And then what? This should be the last one. 60? Okay, well, if the numbers aren't exact, that's okay. The idea is to get the back to front so that you understand what's going on. So then we're going to return that up here, right? And then we're going to, so that's going to be the list. And then we're going to print that out, right? We'll print out the whole list, right? Okay. So now what happens, we call back to front. So let's bring that list down here. And I want you to tell me what's going to happen in here. So is front null? Is front next null? Okay. So we're going to make a new temporary node, which is the front. Is the next node null? So, what?
What would that be?
What would what be? So, okay. So yeah, so temp starts out at front, which is 60, right? So now it's next. So what's next after 60? Okay. And is the one after that null? Okay. So then we're going to update it again to the next 40. What is it going to be when it exits the loop? 10? Okay, so now we have a 10. So we've got this one right here. So if we go down through that, new front, so now we have a new node. So new front is going to be equal to temp-next, which is what? Okay, so this is 0. So now temp next is null, so 0 is no longer at the end of the list, right?
It's the only thing left, isn't it?
We just said that
Oh, wait, no.
the temp next is null, so that doesn't point to that anymore. And now new front next equals front, so what do we put in front of the list now? 0? Okay. And then we return new front, so this becomes our list, correct? So then we're going to print this out. Do you see that? Okay, so let's run it and see if that's what happens. And again, what I'm doing here, going through and building these lists and like writing it, like you know how I'm making these comments, since he lets you write on the tests, you guys should, when you get that test and you see these code questions, because they will be linked lists, build those lists with your nodes, write them on the test, and like move your arrows around when they're making things so you physically have that list right in front of you so that you don't, you know, mess up the order. That's what I'm trying to do, show you guys the physical thing. Okay, so I ran it, and this is what we, oh, I did not change the thing. Or no, I didn't run it, did I? I didn't run it. Okay. So, oh wow, the numbers were right. Well, I just didn't think it, when I saw it earlier, that it was those numbers. Okay, so 60, 40, 40, 60, 25. 60, 40, 40, 60, 25, 10, 15, 40, 10, 0 is correct. And then when we call back to front, we move the 0 from the back of the list to the front of the list. And that's what we got. Okay? Any questions? This is the last problem I have, so if you have anything, now's the time.
Can we just review the code for back and front? It was a little quick.
Okay.
The last few lines. If you could just run over the last maybe 4 lines back and front.
All right, I will do that again. So you agree that this while loop we have here is going to take us to 10, right? It's going to take us to the node before the last node. So we have a new node pointer that we're making here. It's just a pointer. We're not making a new, we're not dynamically allocating a new node. We just have a pointer, and we're going to point it to temp next, which what's the next node? So that's going to point to the last node in the list, the current last node. And then we have here, we're going to update the value of, the next of the temporary node, so which was 10, right? So our second last node, instead of pointing to the last node, it's now going to point to null. Do you see how we're updating it to null there? So 10 is going to point to null. So we're dropping off that 0 at the end. But we still keep that new front, which is pointing to it, so we haven't lost the node entirely. So then we come down here to new front next equals front. So that 0 is now going to point to 60, which was our front node.
Okay, I see what you're doing.
And then we return that node, that 0. So when we come back up to main, my list equals that node. So now the front of the list is going to point to that 0. So when you start there, it's going to go 0 to the 60. And then we haven't touched the 60. So the value, the next of that is just going to go through back to the 10, which now we've changed to be null. So it'll now drop off at the 10. So the 0 has moved from the back of the list to the front.
So you say when you do my list equals back to front there, it only brings the 0 when you return to front.
Right, so it only just moves the 0 to the front of the list. So it returns the 0, which is, that's the only thing it returns, right? And that node, knowing that node, will point you through the entire thing if you traverse it.
Wasn't the second to last command of back and front to put 0 onto the entire list?
Where?
New front next equals front.
Right, so our old front is 60, right?
Yeah.
So we point 0 to 60.
And then you would only return 0.
So you only return the 0. Because you only return one node. But knowing that one node, since it's pointing to 60, gives you the ability to point through the entire link. So like I updated here, see how I put the 0 in front there? You can follow its next pointer to get to that 60, which was the old front. And then you can follow that 60's next to get through to the rest of the list that we had before. Does that make sense?
I still don't understand when you do new front pointing to next equals front, you're pointing 0 to 60 to the whole list.
Yeah, because 60 points to the rest of the old list. So you point the 0 to the 60, so that puts it in front of the rest of the list.
And then you return new front,
Which is the 0, which is the entire list. Because the 0 is the front of the list, so that gives you access to the entire list.
Okay, so then when you go back up to the main function, than
Right.
what we just returned.
Yes.
Then you return the entire thing in that whole command.
Yeah, essentially, because you're returning one node which has, through its next pointer, access to the entire list.
I thought we were just tacking on 0, you set it equal to the
No, you return, you change the value of my list, which is the head pointer for the list. Okay, well, that's all I have. So if there's any other questions, now is the time to ask. Other than that, I mean, there's a survey which you guys can take, which we'd really appreciate it if you scan this QR code up here, or if you have the schedules, they should also have the QR code on it. So if I could get you guys to do that, that would be great. Don't just give me a good review. Be honest. And if you need help studying for the exam more, look back through the, if you need more practice with the scanning, look through this again and follow through. Pause the video before I start doing the scan and scan it again by hand on a piece of paper or something. Yes, it will be on YouTube. It is, yes. Well, sorry.